The next thing we're going to do with vectors is we are going to talk about how to add vectors. And the main method we're going to use in this section will be what you should have used in physics, and that's going to be what's called the head to tail method. So when we go through and add these, the way we do a head to tail method is that we will be looking at where the first vector started, and we will look at where the last vector ended, and head to tail, or sometimes called tip to tail, you will start your resultant vector where the first vector started, and you will finish the vector where the last vector stopped. And this would be true no matter how many vectors you're adding together. And this is very similar to the exercise that we did the other day in class. So along with adding our vector and looking at the resultant vector, we are also going to be looking at how to find the magnitude and how to find the direction angle. That's going to be the next thing that we do here. Well, if we want to find the direction angle of the resultant vector, we always use the trig function tangent. And remember, tangent is opposite over adjacent. And then we'll have to do that inverse, because we will have tangent theta equals opposite over adjacent, but we are solving for theta itself. So we would need to do the inverse theta to both sides. Now we need to make sure our calculators would be set in degrees. That is important. And just a little bit of quick review here. If you're looking for which side is opposite, which side is adjacent, please remember it is from the point of view of your angle. Now, in order for us to also find the magnitude of our vector, the magnitude will be the distance formula. And a little bit of reminder about the distance formula, and let's see, we got some space down here, we can write that in. If we're talking about the magnitude of a resultant vector, that magnitude of the resultant vector is really going to be just like our distance formula that you saw back in geometry and on some of your ACT reviews. It's going to be x2 minus x sub 1 all squared plus y sub 2 minus y sub 1 all squared. So, and inside the parentheses here, it really is not going to matter as far as the order, because you will be squaring it, and so any sign issues that you may have is not going to really show up. Let's make this one a little bit better so we can read that. So that's going to be our magnitude. It's going to be really your distance formula. And then your direction angle here, we're going to be looking at it as inverse tangent. So let's do some problems. You will have these problems on a handout in class. All right, so for our first example, we have vector u, and vector u has a magnitude of 3 miles and is directed due east. So 3 miles directed due east, we are going to start at the origin, and we're going to go 3 miles due east. So we're going to have something that looks like this. And then I'm going to have another vector, and it's going to start where this one stopped, and it has a magnitude also of 3 miles, but is directed due north. So I'm going to start here, and we're going to go 3 miles due north, so somewhere in there. And so I have that vector. So let's look at our values of our vectors. We had 3 miles here. We have 3 miles here. And it wants to know what are the magnitude and direction angle of the resultant vector. So our resultant vector is going to be the vector that starts where the first one started and stops where the last one stopped. So we're going to have this as our resultant vector. And that's normally noted in R with the weird looking symbol above it. Now, if we want to know what the magnitude of our resultant vector is, then we really need our distance formula. So the magnitude of vector R is going to be the square root, and how long was one of the sides? 3 squared, plus what's the distance of the other side? 3 squared. And so our magnitude here, that's going to be the square root of 18, or that's going to be 3 square root of 2. So that tells me that the length of this resultant vector right here is 3 square root of 2. And I'd rather y'all leave it in exact form. Now, a little bit of reminder, how in the world did I break that down? Remember 18, well, I can take the square root of 9, and 9 goes into 18 2 times. And so when I take the square root of 9, it comes out from under the radical, and that's where that one is. That's where the 3 came from. Right, now we need to do our direction angle. And keep in mind the direction angle, well, that would be this direction right here. What's that direction angle? And this is where we're going to need our inverse tangent, but we're going to write it all out to start with, and then we'll probably skip some steps here. But that direction angle is going to be found by saying tangent of that angle theta is equal to opposite, so that side's my opposite, over this side here, which is my adjacent. And so I get 3 over 3. And in your calculators, you're going to do an inverse tangent, because here I need just that angle. I don't need tangent of that angle. So I'm going to say theta equals inverse tangent of, well, 3 over 3 is 1. And so this is really saying tangent of what angle gives me 1, and that what angle should be 45 degrees. So my direction angle is 45 degrees, and the magnitude of my resultant vector is 3 square root of 2 miles. Okay, very similar on the second problem. We have a vector u, and that vector u has a magnitude of 5 feet and is directed due south. So we have 500 feet directed due south, so I'm going to put that down here at a 5. So we have 500 feet due south, and then we have a vector v that has a magnitude of 500 feet and is directed due west. So we're going to have here, and we're going to go due west another 5. So we're going to have our n right here. And again, the same question, what would be the magnitude and the direction angle of our resultant vector? And our resultant vector would start where this vector, first vector started, and end where the last vector ended. And so here is my resultant vector r. So this first vector was 500 feet south, and we had 500 feet west. And so if we need to know what the magnitude is of that resultant vector, well, again, the magnitude of that resultant vector r is going to be the square root of 500 squared plus another 500 squared. And so we're going to end up with our resultant vector, after we simplify all of it, is going to be 500 square root of 2, which hopefully is starting to look kind of familiar as the other problem did, the first one, because these are our special right triangles. This is a 45, 45, 90 right triangle. So if you remember those, then that's going to make this a little bit easier. But if not, you do have your calculator to simplify it. Just try to make sure you keep it in exact form, because that's how you would normally see it. Now, if we wanted to know the direction angle, Well, this is where it can be a little bit confusing because we're looking at this angle in here. And I did just say that that angle is 45 degrees. Now the why it's 45 is because, again, if you're looking for that direction angle, you're going to say tangent of that angle, so of that angle theta, is going to be opposite over adjacent, which, just like the previous problem, it is going to simplify down. We're going to say theta equals inverse tangent of 1, which is going to be 45. But now this is where we have to be very careful. Look at the quadrant that we're in. Now this direction angle that we need is actually starting in standard position, so it's here, and it's going to swing all the way around to here. So to figure out what that should be, if we remember what talks about 45 degrees in the third quadrant from our unit circle, then we're going to realize that it's 225. But if we don't remember that, keep in mind from here to here is 180. 180 plus this 45 that we found will also give us 225. So our directional angle that we need is going to be 225 degrees. And again, the resultant vector is 5 square root of 2. All right, so again, we have a couple of vectors here. We have vector u that has a magnitude of 5 square root of 3 feet and is directed due west. So 5 square root of 3. We have something going out. Let's see, 5 has the square root of 3. So that's probably out here somewhere. Somewhere out in there is a good guesstimate of it. So we have 5 square root of 3. And then we have another vector that magnitude of 5 feet and is directed due north. So 5 feet and is directed due north. So here's my other vector. That is 5 feet. And now I need to find the magnitude of our resultant vector. And our resultant vector will start where the first one started and end where the last one ended. That's our tip to tail. So there's our resultant vector R. Now, in order to find that, well, these values look awful familiar. We have a 5 and a 5 square root of 3. So let's see if we can remember some of those tricks. That special right triangle. Let's see if we had, we had 30 is up here and 60. Hopefully we remember these. And we had 1, 2, square root of 3. And we really could just make this into a formula by saying 1 times x, because if we multiply it all by the same amount, well, that works out to be nice and neat. So it looks like possibly that my x value here is 5. And so my resultant vector should be 2 times 5, or 10. So the magnitude of my resultant vector should be 10. Now, if we don't like doing it that way, we certainly can go through and say, well, that's going to be the square root of 5 squared plus, well, 5 root 3 squared. 5 squared is 25. And then the square root of 3 squared is 3. So it looks like I get the square root of 100, which is 10. So either way you want to do this will be fine. If you remember those special right triangle values, it will be a lot faster for you. And the same is true here with trying to find our direction angle. Well, the direction angle, we knew that was 90. And notice that value of x is across from the 30-degree angle here. So here's 30, and that is across from, or opposite, 1 times x. So we could line that up here and say, well, I know that has to be 30 degrees. if you don't want to use that, again, we could go back and say that tangent of theta equals, and it's going to be opposite over adjacent. And so then we end up with theta equals inverse tangent of 1 over square root of 3, and that again is going to generate 30 degrees for us. But again, this is tricky like the other problem was. We have to really keep in mind that my direction angle is starting here and it's swinging all the way around to here. So we need that particular angle. And either on the unit circle, you can ask yourself, well, what has a reference angle of 30 degrees in the second quadrant? Or you can remember that all the way around from here to here is 180, but we really only need to go this distance here. So 180 minus 30 is 150. So my direction angle here is going to be 150 degrees. Right, now on part D, we have a vector u that has a magnitude of 300 miles and is directed due east. So we have 300 miles directed due east. If I can get my marker to right. Okay, and then I have a vector v with a magnitude of 300 root 3 miles, because that's just a normal way of telling distance there, I'm sure. And that is directed due north. So my next vector, 300 root 3, that is going to be somewhere up here. Okay. And again, we need to find our resultant vector. And that resultant vector is going to start where the first one started and stop where the last one stopped, tip to tail. And so let's see again. Our first one, we had 300. And then we had, this one was 300 root 3. And we need to find that other side. And again, we can go through, if we remember our special right triangles again, we can go through that and see that we have this, and let's see, we could put our 30 up here, and we put our 60 here, and we had 1, 2, root 3, and make it a formula, so multiply all of it by the same amount. So we're going to throw in an x. And so let's see, how can we apply that to over here? Well, it looks like my x value is 30 degrees. And what does it look like our direction angle is? Well, let's see. We've got this here, so our magnitude, let's go back to our magnitude of our resultant vector. It looks like our magnitude is really going to be that hypotenuse, which is 2 times x, and our x value is 300. So that's going to give us 600, or you can do the Pythagorean theorem, and that will also generate that same value. And then our angle itself, our direction angle, is going to be from here to here. And that direction angle looks like it's across from the root 3, which is going to be 60. So my direction angle is 60 degrees. All right, for our next problem, we have vector u, and it has a magnitude of 9 centimeters and is directed to the right. So we have 9 centimeters directed to the right. So we have something like this. Okay. And then we have vector v that has a magnitude of 9 square root of 3. And it is directed downward. So 9 square root of 3 directed downward. So it's going to be way down here somewhere. Okay, and of course that's not drawn perfectly. Yeah, give up on that. But I know that's 9 square root of 3. And so now I need to find, again, the magnitude and the direction angle. And I need to start where this one started, end where this vector down here ended, and connect those two. Hey, that's a pretty good arrow for me. Yay! Celebration time. All right, so again, we can go back to our 30, 60, 90. And I think we've pretty much well got that's the idea of x, and x root 3. Right here's our 90. And so it really looks like my resultant vector here is going to be 2 times x, which is going to be 18. So I think my resultant vector, the magnitude of that resultant vector, is going to be 18. Now, as far as the direction angle, well, let's see if we can reason through and see what that is. Let's see, our direction angle. Well, the real angle that we need is this one all the way around here, but we only have enough information to find this one, so we have to find that one first. Well, which angle is across from the root 3? And that's going to be our 60 degrees. So I know this angle is 60, but I only need what's in yellow, so I know all the way around is 300. So I'm going to back up 60 degrees, and so that's going to give me a direction angle of 300 degrees. Okay, for the next problem, this one might be a little bit different, so we need to be careful here, of course. We have a vector u that has a magnitude of 15 meters and is directed to the left. So 15 meters and is directed to the left. So we're going to go way out here, 15 meters. And then I have a vector v that has a magnitude of 3 meters and is directed to the right. And remember, a lot of times students want to go back to the origin and go right 3 meters, but that's not how we've been doing these problems. We start our other vector where the first one stopped. So if we go back 3 meters and stop, and this is my 3 meters, well, my resultant vector will start where the first one started and stop where the last one stopped. Well, how strange is this? It would start where this one started, and it's going to stop where this one stopped. So it's going to be this region here. So what would be the magnitude of that resultant vector? Well, the magnitude of that resultant vector, since it is a distance, is just going to be 15 minus 3, or 12. So that one is not that difficult of a problem, but it is one that can be very tricky. So again, we found that magnitude to be 12. Now what about the direction angle? Well, the direction angle is going to be from here to here. So that direction angle looks like it's going to be 180 degrees. So this time we did not generate a triangle, but it's quite okay. Okay, here's another one that's very similar to the one we just looked at. Vector u has a magnitude of 3 centimeters and is directed upward. So we have 3 centimeters directed upward. And then vector v has a magnitude of 11 centimeters and is directed downward. So we're going to start where this one stopped, and let's see, this was 3, but then I'm going to go 11 back this direction. So now we've got to look and see, well, what's the magnitude of that resultant vector? Well, we need to start where the first one started and end where the last one ended. So it looks like if we start where that one started, the first one started, and end where the last one ended, it looks like the magnitude of that resultant vector is going to be 8 centimeters. And my direction angle from here all the way around to here, it looks like it's going to be 270 degrees. All right, this one's very similar to the previous two, but now we're told that we have a magnitude and a direction angle. So we have a magnitude of 10 inches and a direction angle of 45 degrees. So we're going to have something like this. Okay, so again, that's about 45 degrees. We have 45 degrees. And we have a direction angle 45 degrees, and we have a magnitude of 10 inches. But then we have another vector v that has a magnitude of 10 inches and a direction angle of 225. Now again, don't be tempted to go to the origin and do this for your 225. That is where 225 is, but we have to start where that first vector stopped. So we're going to come back here. Well, 225 degrees in the first quadrant is exactly the same as 45 degrees. So we come right back. So notice that for my resultant vector, well, there's really nothing to draw, because if I start where the first one started and stop where the last one stopped, I'm right here at the origin. I'm at a point because I went the same distance as I came back. So this one, my magnitude of my resultant vector is 0. Well, what about a direction angle? Well, a lot of people like to say it's 45 degrees because I use that in this problem. But notice I'm just at a point. And does a point, can we really classify that as one specific angle? Well, we can, because you're sitting at the origin. So your direction angle really could be any angle. And so we have to be careful with that. Any angle would work in this case. Okay, for the next one we have vector u. It has a magnitude of 10 square root of 2 meters and is directed southwest. So here's west, here's south. So southwest is somewhere right there in the middle, and it is 10 square root of 2. And again, we've stopped right here. And vector v has a magnitude of 10 meters and is directed eastward. Now again, we have to start where this one stopped, and we have 10 meters eastward. So here's 10 meters eastward. And now I need to know what's the magnitude and the direction angle of the resultant vector. So where in the world would that possibly be? Well, let's go through and see. Well, I need to start where the first one started, stop where the last one stopped. So I have something like this. There's my resultant vector. Well, this looks like it might be, our hypotenuse is 10 root 2. And this side is 10, and this is a right angle. So it looks like these base angles might be 45 degrees. And so if this is 10, then I know this side over here has to also be 10. So that tells me that my resultant vector from my special right triangles, if I remember those, that's going to be 10. Now, if you did not remember that, again, we can use our Pythagorean theorem, and let's go through that, because this time we have the hypotenuse. So we have 10 square root of 2 squared, that's our C, because it's the hypotenuse, equals 10 squared plus a missing side squared. And so 10 square root of 2 squared, 10 squared is 100, times the square root of 2 squared, which is 2. So that's going to give us 200 equals 100 plus x squared. And so when we finish all this, subtract our 100 and take the square root, we do get plus or minus 10, but we're talking about a distance. So we need x to be positive 10, which is what we got if we use our special right triangle facts. Now for our direction angle, again, we're starting here in standard position, and we ended up all the way to right here. So it looks like our direction angle should be 270 degrees. All right, for the last example, we have vector u that has a magnitude of 24 miles with a direction angle of 150 degrees. Now 150 degrees is in the second quadrant and it's going to be somewhere over here. So we have 24 miles and we have a direction angle of 150 degrees. Vector v has a magnitude of 12 root 3 with a direction angle of 0 degrees. So again, that one sounds weird, but if we start where this vector stopped and then we go 0 degrees, that's really just due east again. So it's going to be something like this. So we have this weirdness going on. And we said that was 12 root 3. So if we remember our characteristics of our special right triangles, let's see, if that was 12 root 3 and this is 24, then this side right here probably has to be 12. So that tells me that my resultant vector, or the magnitude of that resultant vector, is 12 miles. And if we look at a direction angle, now again, the direction angle, you start in standard position and we're going to go to that vector, which is right there. So it looks like the directional angle is going to be 90 degrees. If y'all have any questions about any of these, please feel free to ask me in class. I will be happy to help you.